long as my voice holds out, we're going to talk about some experiments in spin relaxation. We've spent the last few classes talking about theoretical aspects of relaxation. There are now a very large number of references or review articles about applications. So I've just listed a couple here from my own laboratory, but there are other very nice ones from Louis Kay's group, Pat Lauria's group, and others. And this is for your reference. And we'll talk today about a series of different experiments. The first will be under the rubric of laboratory frame relaxation techniques. And primarily here, one is interested in what are called generalized order parameters, diffusion tensors, and to a lesser extent in the past, but more in the future, internal correlation times. And then rotating frame relaxation techniques, we're interested in chemical exchange phenomena or conformational exchange. And these split nicely then. The first case are experiments that are driven primarily by rotational tumbling, and that process is fast enough that the Redfield equations apply. And then the second set of techniques, rotating frame techniques, the Redfield equations may or may not apply, and we may have to switch to other methods that we talked about, such as the Bloch-McConnell equations or numerical simulations. We won't really have time to, in today's lecture anyway, we may get to it in a future lecture, about techniques such as amide proton-solvent exchange or averaging of couplings that also provide information about conformational fluctuations, but don't so easily provide time scales. The nice thing about the first two categories is one, at least in theory, obtains information about time scales of processes. So why do this? Probably next class we'll talk about structure determination, and one of the issues that comes up in structure determination when looking at the degree to which a given part of the structure agrees well between different calculations or different members of the ensemble. The question comes up, if a region is disordered in the ensemble of calculated structures, does that reflect real dynamic properties of the molecule, or does that reflect regions of the molecule where you just don't have enough data to restrain the structure? So one case is interesting, the other case means the graduate student has to go find more nosy peaks in the spectrum. So relaxation measurements distinguish these cases. From the standpoint of biophysics, conformational fluctuations are central to statistical mechanical theories of molecules. So we can be quite interested in the fundamental standpoint in aspects of kinetics, energetics, mechanisms of fluctuations. And then, of course, we hope that there's connection to biology. I once told someone that I was interested in dynamics of proteins, and they told me that meant that there were 3 problems I could work on: protein folding, molecular recognition, and catalysis. I've kind of split molecular recognition into ligand binding and allosterism, but you could lump them together and say that that person was right. So there's a small number of big questions, and we try to work out how they come to bear in particular protein molecules or DNA molecules or RNA molecules. Motions in biological macromolecules happen over a very wide range of time scales. I don't even show on here bond vibrations, so bond vibrations are 10 to the minus 14th per second, 10 to the minus 15th per second. But then the picosecond to nanosecond time scale will cover processes out to the tumbling time of the molecule. The size molecules one works on in solution typically tumble with rotational correlation times of tens of nanoseconds. And these will be studied then by so-called laboratory frame relaxation measurements, and in the simplest case, R1, R2, nuclear Overhauser effect, and then possibly more complicated cross-correlated relaxation effects. Out on the microsecond to millisecond range of timescales, then, we'll have the Carr-Purcell, Gill, R1 row experiments that we've talked about already. One can do line shape analysis, which we've talked about. We've talked about magnetization transfer, which is the same as ZZ exchange. We'll talk a little bit about CEST at the end of today. As I said, we're not going to talk about amide proton exchange. And we won't talk today about residual dipole couplings in solution, but hopefully we'll come back to those. So there's a very wide range of timescales, but there's also a very wide range of NMR experiments. All of the pulse sequences will have the same block structure. There'll be an initial preparation period in which some non-equilibrium state of the density operator is prepared. Then a relaxation period where the density operator starts to relax back to Boltzmann equilibrium. And that's the whole relaxation experiment. The rest is just, the other blocks are just to generate a two-dimensional or three-dimensional NMR spectrum so that we can resolve individual resonances. So this block T1 mixing acquisition could be an HSQC sequence, it could be a TROSY sequence, it could be turned into a 3D HNCO. None of that is particularly important. That's all about resolution and sensitivity. It's the first two blocks that are important. In some cases, as you'll see, the labeling period and the relaxation period might be exchanged. I'll mention that again when we get to such sequences. So the experiment will be run once with some value of T. Here's an NMR spectrum, and then the intensity of the peaks reflect the relaxation, how much the density operator has relaxed from its initial state when T is equal to 0 out to a given value of T. So if we pick some peak, I don't know which one, let's say this one, repeat the two-dimensional experiment over and over again with different values of T, measure the intensity in each spectrum, we can then plot the intensities versus T and then fit an appropriate equation to get the relaxation rate constants out. And much of the process of designing the experiments is to try to generate intensity profiles that are easy to fit to obtain a rate constant accurately. So that typically means that we're trying to isolate a small number of possible contributions to the decay and suppress contributions to the decay that we're not interested in so that we can fit a very simple expression. And in this case, these data were just fit with a single exponential decay in order to obtain a rate constant. Dave Case, who is a professor at Rutgers, is a theoretical chemist who works a lot in NMR, likes to tell me that NMR spectroscopists go to great lengths to design complicated experiments in order to obtain data that's simple to analyze, whereas a computational chemist would do a simple experiment and then do a complicated analysis of the resulting data. So sometimes I think he might be right, but as you'll see, most of the experiments are going to be very complicated pulse sequences. So when we look at data in these days, one almost always needs to acquire data at different magnetic field strengths. As for the fast time scale processes, where we're measuring R1, R2 NOE, we now know that we should acquire data at least 3 different magnetic fields to fully extract information from the data. And if 3 is the minimum, that means we would prefer 4 in order to have some extra degrees of freedom in the statistical analysis. So that's a lot of magnet time. At the concentrations at which solution NMR experiments are done, there can be a tendency for proteins to weakly self-associate. So at 200 micromolar sample concentration, if the equilibrium constant for dimerization is a millimolar, there's still going to be a few percent of dimer in solution, and that impacts on the analyses. So it's always useful early in one's work on a given molecule to dilute the sample, run a transverse relaxation measurement, and make sure that one is working in a regime in which the relaxation rate constants are as independent as possible of solution concentration. Many of the processes are going to be very temperature dependent. Overall rotational tumbling, for example, is very temperature dependent because the viscosity of water is very temperature dependent. The chemical exchange timescale processes will be temperature dependent because these are transitions over some barrier. So control of the temperature of the sample is very important. And as you'll see in many of the experiments, as T increases, as the relaxation period increases, the number of radio frequency pulses or the length of spin lock CW RF pulses increases, and that means there's more deposition of RF energy into the sample and therefore potentially more heating of the sample. So modern experiments all try to include compensation pulses. So during the recycle delay between transients, while the system is relaxing back to Boltzmann equilibrium before the first 90-degree pulse, pulses will be included in order to allow a constant deposition of RF power. So during the relaxation period T, as the number of pulses increase, the number of pulses, dummy pulses applied in the recycle delay will be decreased, so that there's a constant number of pulses. But then you have to make sure, of course, that the dummy pulses aren't doing anything that affects the recovery of the density operator back to Boltzmann equilibrium. These compensation pulses frequently aren't shown in papers, so if you're implementing a pulse sequence from a paper, you probably are going to have to figure out on your own where the compensation pulses are going to go. Or if you're sent a pulse sequence by somebody, you're going to have to look in the pulse sequence and make sure that there are compensation pulses. And then the spectrometer room needs to have its temperature controlled. There are components of the instrument, and probably these days, most importantly, the cables that lie on the floor have temperature coefficients. So if the room temperature changes, the RF transmission coefficients change. And that means essentially as the room temperature fluctuates, the probe is going a little bit in and out of tune. The sample temperature isn't being affected, but the probe is detuning a little bit. And that means the pulse lengths aren't exactly what you think they are, and that leads to intensity fluctuations. So we know that if we were to go back to this kind of curve and measure these data over a day where our room temperature is fluctuating because the building is having a hard time equilibrate. This happens at Columbia frequently at this change of seasons when the air conditioning and heating aren't well balanced. So the room temperature could change so substantially during one of these experiments. And then you would see substantial scatter of these points away from the fitted curve, depending on how out of tune the probe got. So we now monitor the room temperature, and if the room temperature has gone crazy during an experiment, we just throw that data away and recollect it, unfortunately. Oh, what just happened?
Auto update.
And then at the end of the day, one is almost always comparing analyses between one or more different states of the sample, with and without ligand, different temperatures, wild type versus mutant, and your ability to make comparison is going to depend on error analysis. So one needs to know what the uncertainties are in the measurements, and that means you need to acquire as many duplicate measurements as you can and then do careful error analysis. We have generally found over the years, as we've collected more and more data on the same system, that we hardly ever have overestimated the experimental uncertainties. We've almost always underestimated them. It's a bit of a warning. I should say about controlling sample temperature, this becomes even more of a problem when you work at two or three or four different magnets, because if you have temperature compensation pulses in the VT unit and lots of dummy scans, the VT unit will stabilize the temperature and will be pretty good at maintaining that mean temperature. But that mean temperature may be slightly different than it is on another spectrometer, even though you think you've set everything up the same. And what we have found to be the best is acquire the spectra, two spectra, overlay them, and adjust the temperature by tiny bits on the second magnet until the spectra absolutely superpose. Any slight difference means that there was a difference between the sample temperatures. Okay, so first we'll talk about the called fast time scale dynamics. The best developed sets of experiments are for the backbone NHs and for deuterium in carbon-13 CH2D isotopomers. That said, there's now ever increasing numbers of experiments that have been developed, so you can go to the literature and find many more experiments. I'll just talk about these two as kind of prototypes of the whole field. So as you know already from the theory that we did, the rate constants, R1, R2, the NOE, etc., are all linear combinations of the spectral density, J of omega, at the eigenfrequencies of the spin system. So our goal is going to be to measure enough relaxation rate constants to characterize J of omega, and then once we know J of omega, to try to learn something about the underlying dynamic properties of the system. That seems simple enough, but remember, what was J of omega? J of omega was the Fourier transform, i.e. the integral, of a correlation function, and the correlation function was the ensemble average of the fluctuations at two different times. So we're trying to learn about the fluctuations, but we're looking back through two kinds of averaging processes. an integration and an ensemble averaging. So even if we know J of omega, we're going to be faced with the difficult problem of how do we go from J of omega to a description of the actual physical fluctuations that the molecule undergoes. And while we won't say so much of it in today's class, that frequently means that one is also doing molecular dynamics simulations and trying to connect the molecular dynamics simulations to the NMR experiments so that the molecular dynamics simulations help flesh out the physical picture. Most commonly, we will use some variant of the Lipari-Szabo model free formalism for modeling J of omega, although again there are other approaches in the literature such as the SLRS theory, slowly relaxing local structure. The experiments all depend on the fluctuations of the stochastic Hamiltonian, but in solution, the stochastic processes are all averaged by rotational tumbling. So fluctuations that are slower than tumbling are barely going to contribute to the measurements. So even near rotational tumbling, one needs lots of data and very high quality data to characterize internal motions that are similar to tumbling. So mostly one is thinking about motions faster than overall tumbling. We'll have two choices. One is to fit a model like the Lipari-Szabo model directly to the rates, or the other approach is to calculate the spectral density function and then fit that, or calculate values of the spectral density function and then fit that. The latter approach is particularly visual, which is nice, and is particularly useful for data at more than one field, but at the end of the day, both approaches generate the same results. R2 can be problematic because R2 could have contributions from both overall rotational motion, fast internal motion, but also chemical exchange motions on a slower time scale. So if we're trying to interpret the fast motions, we need somehow to separate out the exchange contribution to R2 naught. And there's kind of two more or less straightforward approaches these days. One will be to measure the relaxation interference rate constant, which is called eta xy, usually in the literature. This is essentially for the N15 measurement. This is the difference in relaxation rate of the narrow doublet component and the broad doublet component, the Trosy line and the anti-Trosy line. And it turns out that exchange broadening contributes identically to each member of the doublet component, and therefore the difference in rate is independent of exchange broadening. So that's one approach. And the other approach is to make use of the B0 dependence of chemical exchange broadening, so that if we have measurements as a function of magnetic field, then we can try to separate out the B0, the dependence on chemical exchange broadening, by looking at the field dependence and the parameter R2 minus 1/2 of R1 is a frequently convenient way of doing that, although not the only way, but the main point is to have data at more than one field. R2 is usually measured by either the CPMG experiment or the R1-Rho experiment. They both in practice mix in a little bit of R1 relaxation, so that needs to be corrected. And there are schemes for correcting them in, I would say the jury is somewhat out about which one is best if you just want to measure R2. With care, they're both accurate. The field will probably switch more towards R1 row experiments, but that's my guess. So here are pulse sequences from a long time ago from Neil Farrow for measuring the N15, R1, R2, and NOE. They all start with or the first two start with an Annette block to transfer polarization from hydrogen to nitrogen. Nitrogen is very low magnetogyric ratio and therefore an insensitive nucleus. So we want to transfer polarization from the highly polarized hydrogens down to the nitrogen. So that's done by this Annette block. And these values of delta you now know, or delta there will be 1 over 4j, so the full evolution period will be 1 over 2j. In the R1 experiment, at the end of this block, this 90-degree pulse transfers magnetization to the z-axis. So transverse nitrogen magnetization gets flipped back to the z-axis. And because of the phase cycling phi1 magnetization, half the experiments will be flipped to positive z, and half the magnetization will be flipped to negative z. The decay happens here during this period, which in that picture is called capital T. And what's going to happen? Well, magnetization isn't at, the positive magnetization isn't at Boltzmann equilibrium because it's enhanced by transfer from the proton. So it's going to decay down to Boltzmann equilibrium. When the magnetization is inverted, it's going to decay to Boltzmann equilibrium. And these equations then would require 3 parameters to fit: initial amplitude, final amplitude, and then the decay constant. And that's pretty inconvenient, but since we're acquiring both, if we subtract the two, this goes to 0. The long time value becomes 0, and we just have to fit an initial amplitude and a damping constant. So that's almost always done in order to reduce the number of parameters and also trying to figure out what this long time scale value isn't so easy. So that's why this looks a little different from the inversion recovery expression that I showed earlier in the beginning of the class. In this sequence, at the end of the Annette period, we have transverse nitrogen, and now here is a CPMG spin echo sequence. It's repeated some block of time, so this will lead to decay as well, and here's just an HSQC detection period. So here we just fit a single exponential with a rate constant R2. In the R1 experiment, there's this block called decouple, and here we have this additional pulse. And the question is, what are they for? The decouple period in the R1 experiment has to take care of 2 problems. First, of course, the decay would not be mono-exponential because there's an NOE between the nitrogen and the attached hydrogen. So we need to suppress that effect. And we suppress that effect by periodically flipping the hydrogen upside down. And back when we talked about the secular approximation, we said the spins weren't so smart. We could think they had a frequency, 2 Z magnetizations, NZ and HZ. We can make these two non-secular. They're normally secular because they're both Z. but we can make them look non-secular by flipping one upside down periodically. So in this block called decouple are proton 180-degree pulses, usually separated by 1/J, so about 11 milliseconds for nitrogen. And that's to eliminate cross-relaxation between the nitrogen and the hydrogen. At the same time, it has the effect of eliminating the effect of cross-correlated relaxation. There's also a kind of longitudinal Troisi effect in which transitions across the nitrogen transition where the hydrogen is alpha and the nitrogen transition where the hydrogen is beta have different relaxation rate constants because of cross-correlation between dipole-dipole and chemical shift anisotropy. And those 180-degree pulses, by periodically flipping alpha to beta, you'll remember hopefully from a problem set that a 180-degree pulse changes I alpha to I beta and I beta to I alpha. So the pulses are averaging then I alpha and I beta, so the different relaxation rate constants across those transitions get averaged, so that we lose this cross-correlated effect, which also would render magnetization decay bi-exponential. Here, we don't have to worry about cross-relaxation because the nitrogen and the hydrogen are separated in frequency by 450 megahertz. So they're never secular in this case, but we do have to worry about cross-correlated relaxation. We have to suppress the fact that the Troisi line and the anti-Troisi line relax at different rates. We have to average those together to get the pure R2. And we're going to do it the same way by flipping the hydrogen periodically from alpha to beta, or beta to alpha. And then the only question is, where do we put the 180-degree pulses? Here, it didn't really matter. It turns out it's better to put space them, as I said, at times 1/J. That's a very small, but it's a small effect, but measurable. Here, the effect of where you put the pulse is very important. You might think we could do it at, for example, why don't I do it here? This is at the end of one spin echo, here's the next spin echo. It turns out that because of pulse imperfections, this sequence has the property of being somewhat compensated against pulse imperfections on the even echoes and not on the odd echoes. And one has to do either average Hamiltonian theory or numerical calculations to see that. But the even echoes are always better than the odd echoes. So this pulse has to occur at the top of an even echo. It doesn't necessarily have to be every even echo. It's shown here as if it's every even echo. That's not the case. Again, it's okay if they're spaced by, say, 11 milliseconds, 1/J-ish kinds of times, but they have to be on even echoes. Otherwise, if they're on this echo, you don't get the compensation against pulse imperfections, and there's a faster decay of magnetization. And then the third experiment is to measure the NOE. The NOE is measured as a steady state NOE. So we want to measure Boltzmann equilibrium and then compare that to the peak intensities when the protons are saturated. Again, the saturation block will be done really with a string of 180-degree pulses separated by 11 milliseconds, 1/J. And then the Boltzmann equilibrium will be measured just by not doing this at all. So we measure the natural Boltzmann population of the nitrogen and then we measure the effect of saturating the hydrogens. And then the NOE is just a ratio of the two. The problem here is we're starting with essentially the natural nitrogen signal. So this is going to be an insensitive experiment. And in addition, we need to make sure the system for the control experiment has come back to Boltzmann equilibrium. So for a typical protein, let's say ribonuclease H, which is 150 amino acid residues, the nitrogen 15 R1 is about a second. So how long should the recycle delay be for magnetization to come back to Boltzmann equilibrium if R1 is a second? In 1T1, if you started an exponential decay in a time equal to 1T1, how much would the magnetization decay? So that would be 1 over E. So now it seems like my phone is locked up. So 37%. So that's not near Boltzmann equilibrium. So how many T1s do you think you need to wait to get back to Boltzmann equilibrium?
5.
Pardon?
5 T1.
5 T1s? So if somebody want to calculate e to the minus fifth?
So
0.6%. So that's probably a minimum. Ray Freeman used to joke, if you know what your T1s are, leave 5. If you don't know what they are, leave 7. And one problem would be, in this case, on average they're 1 in RNase H, but the more flexible sites are maybe longer T1s, and then you need even further, longer time here. But even if you said 5 seconds, that's longer than you're usually leaving. Most of the time you're running just an HSQC, the recycle delay might be 1.5 seconds, it might be 1 second. You're not getting anywhere near Boltzmann equilibrium, but you get enough recovery, you're happy to collect the next transient. But here you really have to wait. But there's a even more insidious process, and that has to do with amide proton exchange. In this case, we're talking about the amide nitrogens. They exchange with, the hydrogens exchange with water, and the water could end up saturated at the end of this experiment because of water suppression. So the amide nitrogen recovery is perturbed by the spin state of the attached hydrogen, because if that hydrogen is saturated, you don't come back to Boltzmann equilibrium, you come back to the steady state NOE. And that the hydrogens can look saturated because they're exchanging with the solvent, which is saturated. And so then you need the water to be at equilibrium, And what's the T1 of water? Probably don't have any idea. The T1 of water is 4.5 seconds. So now you say I have to wait for the water to recover to equilibrium. Now we're waiting a very long time. And two things happen. One is we do wait a long time. Typically this might be 12 or 14 seconds. So the experiment is very inefficient. But then modern sequences will use some water selective pulses in here to try to keep as much of the water on the positive z-axis as possible, in the hopes that we can get back to Boltzmann equilibrium without waiting 5 water T1s. So if we have to wait 5 water T1s, now we're talking about 25 seconds per scan, and the graduate student life gets very, very long. So here are some things, details about the experiment. There's the refocused inept. We generate plus or minus nitrogen magnetization. Relaxation occurs during the period. The initial value is plus or minus because of the phase cycling. So then when we subtract we then can detect. So we have one signal when we put the initial magnetization on the plus axis, another one when we put the initial magnetization on the minus axis, and then we're going to use the receiver phase cycle to subtract those two experiments so that we get this simple decay. This goes on then to talk about the things that we said, or I said. So we want to measure the decay of nitrogen magnetization. We also have Z magnetization. These are secular, and there's an NOE between them. We also have 2-spin order, and this builds up from SZ magnetization because of cross correlation that I called eta here, but it can also build up by cross correlation from the IZ spin, so I called that epsilon here. So we'd like to purely measure R1, but it's coupled by sigma, eta, and epsilon to these other spin states, and they will all have their own relaxation rate constants. So we somehow want to figure out how to render all of these effectively 0 so that the nitrogen magnetization decays with a single exponential. And I told you that we're going to periodically invert the I spins, and then since we periodically inverted them, we know we've made the I spins independent of the S spin. That would be true here too. We'll be inverting this component of the operator. So I put these all to 0, and now I have the desired result. Of course, I can prove that that's the case by doing a numerical calculation. Just more details about the math that we've already talked about. Now, there are remote hydrogens, so the N15 is relaxed not only by its attached hydrogen, but also the remote hydrogens, and the amide hydrogen is relaxed by remote hydrogens. So these are fairly small effects for the nitrogen because the bond length the one bond length is pretty short, 1.02, 1.04 angstrom, and the other hydrogens tend to be fairly far away. It's more of a problem for carbon relaxation where the bond lengths are longer, so the remote hydrogens contribute more. But still, it's the quality of the spectra, the quality of the measurements go up if you can deuterate. And then there are nice pulse sequences from 2012 that basically adapt these pulse sequences for TROSY and assuming deuteration. So those are probably the most modern pulse sequences for these experiments. And here's what data looks like for ubiquitin for 2 different spins. And again, if one controls all of the temperature problems, you can see the duplicates match quite well in these data. So the data are quite reproducible if, in particular, temperature is controlled. And now here's what the data looks like for ubiquitin. This kind of plateau, ubiquitin is a quite well-ordered protein. So this kind of plateau in both R1 and R2 are suggestive of overall tumbling with very limited internal motions. Where there are dips in R1 or the NOE, that suggests enhanced motions, internal motions on the fast time scale. And then points like this are suggestive of probably chemical exchange broadening at those for those peaks, because they're contributions that show up only in R2. One thing that can be tricky just with these data alone is the question of diffusion anisotropy, because if the protein isn't a sphere, R2 will depend on whether the NH bond vector points along a long axis or short axis of the diffusion tensor. And in the early days, there were papers published where people said, aha, in this protein, there's a helix that has some slow time scale motion relative to the beta sheet, but that turned out later just to be that in the helix, all the bond vectors point in one direction. All the NH bond vectors point in one direction, and that direction happened to be along a special axis of the diffusion tensor. So what looked like enhanced R2 from exchange broadening was really just enhanced R2 from diffusion anisotropy. So now everybody knows to be careful about such things. Here essentially is the model-free formalism then for interpreting these data. So if the red is the NH vector, the simplest model or the simplest information you would want to know is what's the amplitude of motion and what's the time scale of motion. So in this model, the amplitude of motion is captured by a generalized order parameter, S, although the experiments give S squared. And then the time scale is given by an effective correlation time. Something's wrong with this picture. It should just say tau sub b. I don't know what these other things are doing there. So here's some data for RNase-H. Here, the spectral densities were calculated. The nitrogen 15 relaxation rate constants, if you look back in the tables in the earlier lecture, depend on J at 0 frequency, at the nitrogen Larmor frequency, the 0 quantum frequency, the hydrogen Larmor frequency, and the double quantum frequency. The 0 quantum frequency is 550 at 500 megahertz, would be 550 megahertz. the hydrogen Larmor frequency is 500 megahertz, and the double quantum frequency is 450. Why is the double quantum frequency smaller than the zero quantum frequency? Because of the sign of gamma. Nitrogen gyromagnetic ratio is negative, so its frequency is really negative compared to the proton. So the double quantum frequency is really the difference, and the zero quantum frequency becomes the sum. But out here, this is out where the proton Larmor frequencies are. The proton single quantum frequency, the double quantum and zero quantum frequency differ by only plus or minus 10%. So it's usual in these experiments then just to replace those three values by a single average value. So this represents, I forget what fields these are at. These are probably 5, 6, and 800 megahertz. So here, this represents an average of the data, or the spectral density at 450, 500, and 550. And this would be 540, 600, and 660, so on and so forth. And one knows in theory that the decay here is quadratic, so the averaging is actually quadratic rather than linear. But that's why you don't see more points out here. Here are the nitrogen Larmor frequencies, one at each field. And now there's 3 J0s piled on top of here. Obviously J0 should be the same at every field. So that's a nice control on the experiments. The analysis at each field should give the same J0. So the fits then are to the Lopari-Szabo equations with more exponential terms, basically. So this first decay is for a quite rigid site, and it's fit with a model that just has overall tumbling, tau sub m, and then an order parameter s squared, measuring the amplitude of the internal motions. And order parameters would be 1 if there was no internal motion. So this is a pretty rigid site. And in fact, the extent of motion is so small that we can't resolve the internal correlation time. So until the internal correlation times get to be about 30 picoseconds, they're essentially unresolvable in these experiments. Here is then a somewhat more mobile residue. And now the dashed line is fit just with the simplest model. And you can see it doesn't fit the data. And now we fit both overall tumbling, the order parameter, and an effective internal time. And now you can see the fit is very good. Remember that this effective correlation time, right, is an area under the correlation function. We talked about this in the last class. And then here's a much more mobile site. Again, dashed line is the simplest model. Small dashes. There's this model, and then the solid line is a model that has 2 order parameters and a time constant for the slow process. And again, the fast process is too fast to be characterized here. What is striking when you compare these different fits? Which data is critical for distinguishing the different models?
Like the center of this curve, more or less. I mean, at the end, it's just a big error, of course, but I mean, other than that, I mean, the beginning
frequencies are all fit virtually identically by all the models. It's the data out at the hydrogen frequencies that are really distinguishing the models. The error here is just because these are old data, and way back when we could get very limited time on an 800 megahertz spectrometer. This actually predates the structural biology center. So today, these would be much smaller error bars.
So it's the MTA, I think, right?
Pardon?
It was just the MTA, people getting played to the center. So
Yes. So the distinguishing the models depends very much on the hydrogen Larmor spectral densities. And then if one looks back at the analyses, that ends up depending a great deal on the NOE experiment. And remember, the NOE experiment is the least sensitive experiment because it starts with natural nitrogen magnetization. So it's not the most favorable situation. The experiment you need the most is the one that's the least sensitive. And then you can see the models diverge more if you go to higher and higher fields. So this is 800. You can see the obvious advantage of having a 900. Here's an example of order parameters now for RNA-seq. They're color-coded on the structure, yellow being low and blue being high. And essentially you learn early on that secondary structure is rigid, loops are more or less mobile, and after you've done that once, it stops being interesting. So what could be interesting is then what happens when you do something to the protein. What happens when it binds the ligand? What happens if you make a mutation? What happens if it unfolds? Here's some data about reproducibility. This graph is either terrifying or reassuring, depending on your viewpoint. So this is comparing data that was collected a long time ago on a single magnet at 500 megahertz, actually by my first graduate student. And then this is the data at 3 fields collected by a graduate student, I think 2 generations later. So this shows the comparison. And the solid lines are the residues where we pick the same model in each case. And the open circles are where we fit different models because we go through a statistical model selection trying to find the model that fits the data best. So the 2 analyses were done independently. So you can see if the same model is used to fit the data, then the agreement is really terrific. But if you pick different models, the agreement isn't so good. And 2 things happened. And one is, and I don't remember which side of the curve is which. I should remind myself. On one side of the curve, one side of the line, the deviations are caused by the fact that with data in one field, it's very hard to tell if there's exchange broadening contributions. So some of the data was contaminated by exchange broadening, and then the fitted results weren't accurate. And then the other side is with data in more than one field, it's possible to fit more complicated models. So there tended to be more data fit with internal correlation times in the data set with 3 fields than 1 field, and fitting more correlation times also affected the order parameters. So one side reflects one difference, the other side reflects another. I don't remember which is which. There's 2 approaches to model selection. If you've studied any statistics, you know that the world of statistics is divided into 2 camps who hate each other. There's so-called frequentist statistics and Bayesian statistics. So choosing between alternative models in the frequentist approach is called F-testing. And the most common of many Bayesian approaches is called AIC. And there's NMR papers applying both methods to NMR data. I don't have a strong feeling about either one. I think both work well if you have good enough data. Now, what can one do with these order parameters? And one approach has been to interpret the fluctuations. S characterizes the amplitude of the fluctuations, and that's related somehow to entropy. Right? Entropy is a measure of disorder. If the vector can occupy many orientations, it's more disordered than a vector that can occupy a small number of orientations. So there's a clear sense that something is related to entropy in the order parameters, so that if the order parameters change before and after a ligand binds, that should tell you something about the entropy associated with the binding process. So there are a number of approaches in the literature. This particular formula is due to Lewis K. So it says if we take the order parameter for the apostate and compare it to the liganded state in this equation, and then sum up over all of the residues, we get an estimate of the change in entropy of the molecule upon binding of the ligand. So these are the papers that kind of started the idea, and here's a simple case. Calbindin is a small protein that can bind 2 calcium ions. And here is a plot of the order parameters for the apoprotein and calcium bound. And you can see while most of the protein is fairly similar, there's a huge difference here between the apostate, where the binding loop is very flexible, and then it becomes rigid when the calcium binds. And then one can calculate an estimate then of how many kcals per mole of entropy it costs the protein to rigidify that loop. This has been turned into a quite powerful approach by Josh Wan's group at University of Pennsylvania. They've been able to calibrate this approach against calorimetric measurements of entropy for a series of peptides binding to calmodulin. So calmodulin, you probably know, binds an enormous number of different peptides from different proteins. So Josh's group has measured calorimetric binding and relaxation data on a whole series for calibrating this. And then Babis Kalodemus's group, when he was in Minnesota, did the same thing with a series of mutants of a protein I can't remember, and also showed really very, very striking results. Okay, I left out somehow, maybe it comes up later, maybe not. I left out perhaps the other main application, and that is, of course, one could be interested in the change in overall tumbling. For example, if you have a protein that undergoes some large conformational change in 2 states, say from open to closed, then rotational tumbling is going to change, and one might hope to characterize that change from these experiments. And they turn out to be very, very good at this. We talked about this a little bit last time, that one can measure R1 and R2 and use that to extract the diffusion tensor. Okay, so let's start with slow dynamics in chemical exchange or conformational exchange, and we'll probably continue this next time, I think. So if the lines are resolved for the 2 states, or 2 or more states, then The ZZ exchange experiments or NOZ experiments are powerful approaches. The line shapes are most sensitive near intermediate exchange, but of course that's also where the lines are weakest. So in proteins or nucleic acids, line shape analysis isn't used so much. There are a few papers where it's used quite a bit is if you're able to look at the ligand. So if you have a small molecule ligand that's binding to a protein, then even in intermediate exchange, the signal to noise on the small ligand may be good enough to do fitting. And Dorothy Kern did a lot of this in prolyl isomerases, looking at small peptide line shapes. Tanya Mittag did this as a graduate student with some small molecule binding to some protein I don't remember. And then, as we've talked about, CPMG and R1-row experiments are probably the main techniques used these days. So again, probably obviously changing the system and collecting more data helps increase the information content. Again, it's nice to know R2-0. That's a fitting parameter most of the time, so if you're able to measure it independently, that's a big help. And it's always the case that there's more information available if the system isn't in the fast exchange limit. So manipulating temperature, buffer, whatever, so that you're not in fast exchange or not very fast is usually helpful. The CPMG experiments were made robust first, so there's many more papers applying the CPMG experiment. At this point, they're simple to set up. There's lots of variants of them. The R1-row experiments actually have more information in them because, as we saw in the theory section, they contain information on the minor resonance, not just the absolute value of delta omega. So there's more information in R1-row, but historically they're harder to do, and they don't exist for all possible nuclei yet, or coherent states that one would want to work on. So the CPMG experiment still is very popular, but the R1-row is catching up. You know this, we looked at this last time. So here's a sequence for ZZ exchange. Again, magnetization is transferred from hydrogen to nitrogen, and now it's frequency labeled. The frequency labeling introduces a phase difference between magnetization in the two different sites because they have a frequency difference. So this pulse here at the end is going to flip magnetization back up onto the z-axis. It only flips up one component, say the cosine modulated component. So magnetization in the two states, when flipped up to z, will be modulated by cosine omega t1. And because their omegas are different, there are going to be times when they point in the same direction and times when they point in different directions. And that's what we need for this experiment to work. We need there to be a difference between their amplitudes. If they were always had the same amplitude, wouldn't matter whether they were upside down or right side up, we wouldn't see any net effect. But the cosine modulation means they have different amplitudes and sometimes they point in other directions, and therefore we'll see population transfer. We're going to ignore it, but there could be effects of exchange during the deltas periods, and that might have to be taken into account in order to get the most accurate measurement, and there are ways of doing that in the literature. So here's what I just said. At the start of the relaxation period, we frequency label, flipped up one of the components. I said cosine component, it could be the sine component, it doesn't matter. So this modulation is different for the two. So they're going to have different intensities. And again, we'll have this plus or minus because of the phase cycle. So the cosine factors act like selective inversions. And then we know the phase cycle is going to eliminate the Boltzmann equilibrium magnetization. The decoupling, again, will be a series of 180-degree pulses in order to eliminate the cross-correlation and cross-relaxation effects. So here are the equations. Right? These A's are the elements of an exponential matrix, or a matrix exponential. So those are some complicated functions of the R1s and the rate constants and the populations. That's not so important. So I just plugged in the initial values. And then after the relaxation period, right, we will have magnetization that started on the A state and ended up on the A state. Magnetization that started on the B state and ended up on the A state. Magnetization that started on the B state ended up on the B state. And magnetization that started on the A state and ended up on the B state. So the magnetization is mixed. And now I just transfer back. And I'm going to record the I-spin magnetization. And I'll have so-called diagonal peaks in which the magnetization started on one site and ended up on that same site. And I'll have cross peaks where magnetization started in one site and ended up in the other site. I mean, here's what data looks like. So this is for a protein that dimerizes. Here's the monomer peak, here's the dimer peak. When T is short, we see very little cross peak over here below the contour level. And as T increases, the cross peaks grow in, everything is decaying away because of R1, so everything is getting weaker, but the cross peaks are growing in relative to the diagonal peaks. So one wants to fit these time scales. We could go back here and say the diagonal from the monomer has a time constant given by whatever this function is. The time scale for the dimer has diagonal peak has this decay profile. The cross peaks have these two. We could fit those four equations simultaneously and get out the parameters, the R1s and the rate constants. And that's what's usually done in the literature. However, if you can see both cross peaks, then you can take the intensities and form this function that we call pi. And that's a function of all of these A's, which are very complicated functions, but they reduce to a very simple result, which is just the product of the two rate constants times the time squared. And that's graphed here for two different residues in the protein and fit with a quadratic. So if all four peaks can be measured, this is a great simplification in data analysis. The problem with this simplification is we get the product K12 times K21, and you'd like to know them independently. But of course, the ratio of peak intensities when T is 0 should be just the equilibrium constant, and the equilibrium constant is the ratio of the rate constants. So if we can measure the equilibrium times 0 intensities, we can get the ratio of the rate constants. This experiment gives us the product of the rate constants, and then we can separate the two. We can get the individual rate constants from those two measurements. when will this experiment fail? The experiment fails, right, if the decay of the diagonal peaks is too fast. If R1, if T1 is too short relative to the jump time, because then the signal decays away before the cross peaks can build up. And then there are no cross peaks, and therefore the experiment doesn't work. But as I said, for nitrogen 15, the R1s in a protein like RNase H are about a second. So if the jump times are under a second, the experiment is likely to work. So that covers quite a range of time, although not always. In a mutant of this protein, the rate constants became so slow that we just had to do a rapid mixing experiment by fluorescence. We couldn't find anything in the ZZ exchange experiment. I think that that's probably a good stopping point for today. So we'll finish this up next time. And I will send it, make a PDF and send it to Mike. I don't think I did that yet for this lecture, so that you can look ahead for the next class.